This lecture will be about solving more complex truss systems and some tips and tricks commonly found in university exams and what to look out for to most easily solve for your exam tasks. In the first part of the lecture, we will be introducing force summations at different angles. So in the first part, in our first lecture, we were introduced to summing forces in the horizontal and vertical directions. This first part of the lecture is about solving them at slightly different directions that make sense to you and when you can kind of see that you should do this. Second part of this first section of lecture 2 will be about decomposing forces at more obscure angles. The first method to solve for this truss task is going to be with brute force, with the sum of forces horizontal and sum of forces vertical. And the second method to do this is to take sum of forces in this direction. And I will show you why this one is infinitely superior and much faster and much less likely for you to make a mistake. If I want to brute force it, first thing I have to do is take a cut right there. Okay, I take this cut and I get S1, F, and this bar is not labeled. So with an unlabeled bar, what I always do is to name it alphabetically. We will call those SA, this one is S2, this one is S3, and this one is 2F. These bars you can name whatever you want as long as you're very clear. I think alphabetically is the easiest. Some people like indicating it with this asterisk or whatever. I think this is quite poor because the more bars you have, the more asterisks you have to add, and you're limited to basically like 5 before your equation looks completely ridiculous. Labeling it with the alphabet, I think, is the easiest. And now I will divide this one as bar or block 1, and this part of the system is block 2. Okay, this is just for your simplicity so you can see how I analyze the system more easily. Sum of forces horizontal of block 1 has to be 0. S1, and I'll take right side as positive, times 1 over square root of 2. Factor of 1 over root 2 is because we have a 45-degree angle, and sine of 45 is 1 over root 2, plus f, so they both point to the right, is going to be equal to 0, right? This means that S1 is equal to minus square root 2 of f. Now, I can use this to take the sum of vertical forces, take upwards is positive, of also block 1, and set that equal to 0. So I have S1 times 1 over root 2 with a negative sign because S1 points downwards, minus SA is equal to 0. Once again, I mentioned this in the last lecture, whenever you cut any bar, make sure the forces always point out of the bars, okay? Because in all of mechanics, we always define tension as positive and compression as negative. The positive force has to be if I have a net force pointing out. This is just so this sign convention works, okay? Always define the forces pointing out of the bar. When I move the equation, I get SA is equal to minus S1 times 1 over root 2, right? Subbing in what S1 is, SA is equal to F. Now I will analyze block 2 with this equation. So sum of forces horizontal, block 2, is equal to 0. And this one has 2 unknowns. It doesn't really help me, but what it does tell me is the ratio between these two, because I can use that ratio to solve the question. So S2 times 1 over square root of 2 plus S3 times 1 over square root of 2. Again, both of them point to the right, so they're both positive here. It's going to be 0, okay? And with this, I can say that S3 is equal to minus S2. Importantly, I want to solve for S2, so this equation has to be able to sub out S3. And the final step of our very many step series is the vertical forces of block 2. We'll take upwards as positive once again. From this, I see that SA is upwards, so SA plus 2F plus S2 divided by square root of 2 minus S3 over root 2 is going to be 0. S3 is minus S2, so I can change this to plus S2, and then I have 2 of those terms. So let's go SA plus 2F plus 2S2 over square root of 2 is going to be 0. This is going to be 2 over square root of 2, S2 is equal to minus 3F. S2 is going to be equal to minus 3 square root 2 over 2F. And this is my final answer. So you see, I had to do 4 separate force summations. And if I messed up any signs or any angles in any one of these steps, I would have completely messed up my question. Let me show you the second method, and you can decide for yourself if it's better. Give you a little heads up, it is. And the second method is to take my sum of forces in this direction equals to 0. So once again, in an equilibrium condition, sum of all forces and sum of all moments is 0. Doesn't have to be horizontal and vertical, and it intuitively makes sense, but it's just a little heads up for you that it doesn't. If I take sum of forces in this direction, why does that make sense? It's because my 2 other unknown forces are pointing in this direction, and this direction, with my force sum, is perpendicular. So neither of these forces, these unknown forces, actually have a component in this direction. It doesn't matter that S2 points in this side, the more important thing is S1 and S3 point perpendicular to it. Okay, this is why I'm taking the force sum in this direction. Sum of forces in that direction are going to be 0. S2, which points in this direction, I took that side as positive, plus F divided by root 2. So currently, F points this direction. That's this F, right? This force has a component in this direction and also has a component in this direction, okay? And it makes up this F. And of course, this has to be a 90-degree angle because those two forces I'm decomposing have to be perpendicular to each other. This component, which is in the same direction, that's why it's positive, has a factor of 1 over square root of 2, because if that's a right angle, these two have to be 45 degrees. 1 over root 2, and positive because it points in this direction. I do the same with this force, so this force points upwards, which has a component in this direction and has a component in this direction. Okay? So it's once again positive, plus 2f over square root of 2 is equal to 0. Now I just shove both of these terms on this side, and I get s2 is equal to minus 3 over square root 2 of f, right? Which, in other words, is minus 3 times square root 2 over 2f. And that's done. So I get the same conclusion, but it's much, much faster and much easier. And just in case anyone doesn't know, if I have this and I want to turn it into this, what you do is you just multiply both sides by square root of 2. Okay? So square root 2 times square root of 2 gets me 2, and the top is 3 over square root 2. It's a very good exam tip to actually just look at your whole system and figure out if there's an unorthodox direction that very quickly makes you able to solve the system, okay? Sometimes the mechanics exam will be super difficult and it's going to take a lot of steps and you need to be very careful and it's going to give you a lot of time. Other people will have an exam that's not too difficult but very fast. And for the people who want to solve the question super quickly or do a final check, this is a very, very good thing to do because it's very quick as long as you can see the little tricks. The second thing that I said I would introduce is to figure out how to decompose forces given that it's at a slightly odd angle. Here we can see in a case where my force is not at a 45-degree angle, since my two lengths here are not the same. So how do I decompose this? There's two methods. First one is known as triangular decomposition, and the second method is sine and cosine. Triangular decomposition. How does one do this? The way to do this is to just utilize a triangle. So first thing you do, you draw a triangle. So I will redraw the triangle here. That describes this. I have one with length 1, the other one with length 2, and my last length is L. Now I solve for L directly with Pythagoras. So it's square root of 1 squared plus 2 squared, which gives me square root of 5. Okay. So since my length is square root of 5, that actually is also the magnitude of my force. So my force, since this is 2f and this is 1f, my force, this one, this red force here, has to have a magnitude of square root of 5f. It's equivalent to the lengths. The second method, of course, is sine, cosine, and tangent. For this method, we once again draw the triangle that represents the system. So this bottom length will be 2n, top length is 1n, and we figure out an angle theta here. And of course, the force we're trying to solve for is still this force F over here. So it's this force. So tangent of theta is going to be equal to 1 over 2, right? Both of these forces. Theta gets me an angle of 26.565 degrees. You can verify this with your calculator. Knowing this, I can say that F times cosine of theta will be equal to 2n, or I could also say that F times sine of theta is equal to 1. Both of them work, it's just something that describes this triangle. Either one of these equations, let's just take the cosine one, gets me 2 divided by, let's go with Newton's still, cosine of 26.565 degrees. And this gets me a value of 2.236, which is equal to square root of 5 if you take your decimals perfectly. And this sort of brings me to my point as to why I strongly recommend doing a triangular decomposition rather than doing sine cosine. So in most cases, when you have a question, some part of it will ask for an answer that has a square root or has some decimals. But the thing with the square root that's very advantageous is that in a lot of cases, you can actually cancel the square root later. So if I initially found this f and it transfers forces somewhere else, horizontally and vertically, I can decompose it back into one of these two components. And to decompose something with a square root in it is much easier than to decompose something with decimals, because if I divide this by some value that supposedly has a square root of 5, and it's something like 2 root 5, I might not get exactly 1/2 out of this. I might get something slightly close, but because of rounding errors, it's going to look very weird. With the root 5s, I can directly cancel it. And that's why I very strongly recommend you do this with the triangular decomposition. Before you go, if you want the full uncut version of every lecture right away, they're on my website with the link in the description. The lectures cover all the topics on screen right now. If you found this video useful, please like and subscribe to help the video reach more people trying to learn mechanics. If you want, you can also buy me a coffee on my Patreon with the link in the description of this video. Everything I produce here is done completely from scratch, so these videos take a really long time to make. Thank you.